Okay, great. So the only remaining question is what malware this was putting on my machine. So I wanted to start off by talking about what I mean by a key management network. This is actually something that I talked about last year, and I wanted to spend a little bit of time reiterating that and making some sort of new points, and also following up on some of the points that were made during the fireside chat that we just heard. So I'll compare it to some of the other models for digital asset management, and I'll talk about some potential advantages that I think this model can provide. And then in the second half of the talk, I'll just introduce a new honest majority threshold ECDSA protocol that is particularly suited for deployment in key management networks. So let me first, okay, we all know threshold cryptography is useful for digital asset management. And the core problem that threshold cryptography is coming to address is basically avoiding the central point of failure for the signing key that controls some digital asset. And so to remove that central point of failure, the natural thing to do is to try to use a threshold signature scheme to distribute the key across multiple parties that will store the key, multiple parties that will collaborate in order to sign a message using that key. And there are at least 3 different ways to deploy threshold signatures for digital asset management. Actually, there's even, I was talking to somebody earlier during the break, and there's even a 4th way that I didn't include on the slides, but 3 that I think are pretty common that we've seen in the industry. So the first is what I call shared custody, where essentially the user, represented by the cell phone down at the bottom of the slide, is retaining one share of their key and putting other shares, storing them with some other company or possibly companies that will then have to interact with the user in order to produce a digital signature. And you can contrast that with what I'm calling a key management network or a key signing network, if you like, where basically the user is outsourcing storage of all the shares of their key to some third-party provider or potentially multiple providers as well. So it doesn't have to be only a single provider that's controlling all of the servers holding the shares. You could imagine a scenario where there are multiple providers, each operated by different entities that are holding different shares of the user's key. And then the third model that I've seen is what I call on-premises deployment, where basically the user themselves is using a threshold signature scheme, but there's no third entity, there's no additional entity rather controlling any of the shares. Rather, the user is managing all these servers, whether they're in one central location or whether they're spread around the world, but the user themselves is managing the operation of all those servers and all the entities controlling the shares, but they're using threshold cryptography as a way just to distribute the key and avoid the central point of failure. Now, if we go back to the first 2 that I showed, the shared custody model and the key management network model, really what I think the main question dividing the 2 and the reason why you might pick one versus the other is this question of whether or not you want the end user to be responsible for securely managing a key share. This sort of came up a little bit in the fireside chat with the discussion about whether or not users are able to capably hold keys and not lose them in particular. And more generally, right, is the user better off outsourcing this responsibility to one or more security-focused companies whose full-time job is to securely manage and store those keys? And the argument for the latter is that those companies are better able to implement security controls, things that the user simply cannot or will not do. They can implement monitoring. They can harden their servers. They can do logging to see exactly when the shares are used every time they're used to sign something. They can audit their code. They can patch the code. These are things that are much harder for an individual user to do, and many users simply will not do them. And companies are also better able than users to handle backup of the key shares, also to respond in case there's an event like the loss of a key share, and to recover from any such events that may occur. Now, the counter argument to that is that some people really worry about outsourcing the key, right? This, if it's not your keys, it's not your crypto, and they want to make sure that the end user or they themselves have control of the ability to sign, and therefore they must hold a key share. But I think the reality is, for many users of crypto today, they would actually prefer this sort of a model to the model where they have to actually be in control of their key share, I should say. There are some other arguments, I think, that I think are in favor of the key management network approach. First of all, and this also came up in the fireside chat, is that a shared custody solution, to some extent or another, I mean, this is not entirely true, but at least many of the deployments involve an n out of n threshold protocol. And the reason for that is that if you imagine the user holding one of the shares, and the user wants to make sure that they're in control of the ability to issue a signature, then essentially that means that the user's key share has to be necessary for issuing a signature. You can do other things that are much more complicated that I haven't seen in practice, but the natural way to approach that is to use an n out of n threshold, so that every key share has to be involved every time you want to generate a signature, and that inherently means that the user must also be involved to generate that signature. Now, the flip side of that, and this also came up in the fireside chat, is that if you use an n out of n threshold solution, then you lose availability if a single machine is down. So that means that for whatever reason, any server in the company's network is not available at the moment you want to sign, then you're unable to issue a signature until that server comes back online. And even worse than that, if any of the servers or the user themselves loses any one of these key shares, then that's catastrophic because that means you lost the key. Now, right, and in any event, no matter how you split things and whatever kind of complicated access structure you might use, the loss of the user's key share is also catastrophic, and that's inherent if you want the user to have the ability to determine whether or not something gets signed or not. Now, you can address that, right, by adding complicated recovery mechanisms on top of the threshold protocol, but I think if you look at these things carefully, a lot of these recovery mechanisms end up reintroducing a single point of failure that you were trying to avoid in the first place. In contrast to that, these key management networks that I was talking about can use more flexible thresholds. They're not tied to an n out of n structure. They can use a more general t out of n threshold structure, and therefore they can achieve better availability, right? You can still sign even if one machine is down, for example, as long as t is less than n. And moreover, if any of the servers does end up losing a key share, you can recover that key share directly using the other parties. You don't need sort of a complicated, or I should say, you don't need a recovery mechanism that goes outside what the threshold protocol itself can provide. You don't need to design anything on top of the threshold protocol, differently from what you're already doing, essentially. Good. Oh, and let me just say, actually, that you can do kind of a simple calculation. You can determine, right, because a lot of times people focus only on the question of robustness to adversarial corruption. And they think, therefore, okay, well, increasing T, if we're doing a T out of N signature, then higher T is always better. And that's not quite true, because what it leaves out is exactly this calculation about availability. And so you can do the calculation, you can come up with what you believe are reasonable probabilities for the probability that any given machine will be attacked by an adversary versus the probability that a machine will potentially be down or potentially lose the key due to data corruption. Presumably, the probability of the latter is strictly higher than the probability of the former, because in particular, an attacker who compromises the machine could choose to delete the key. And you can do the calculation and determine basically what is the optimal T and N if you want to achieve a given level of availability versus a given level of robustness to adversarial compromise. And if you do that calculation, depending on the values you choose for the two probabilities, you may end up finding that a lower value of T is actually giving you, quote unquote, better security overall when you take availability into account. Now, when we talk about these key management networks, one of the things that's interesting about them is that if you look at the treatments of threshold cryptography in the literature, all of the treatments that I've seen focus on the case of a single user distributing a single key among n parties, right? So you have somebody who has a key, they want to distribute it, so they distribute it among some various n parties. And the users who are sharing these keys, usually there's only one if the paper talks about a user at all. But if there are, if you imagine extending this to other users also sharing their keys, then at least it's left implicit in the paper, but I think the understanding is that those users may end up choosing different sets of parties. And even if they tend to choose the same set of parties, the protocol executions that are taking place to generate signatures are independent of each other. So you may get some security guarantees, like composability guarantees, even if you have multiple executions of the protocol running among the same set of parties, possibly concurrently. But the point is that the executions are independent, and they're not taking advantage of potential efficiency optimizations that they could get by actually coordinating those executions in some particular way. Whereas in a key management network, you actually have a dedicated set of end parties who are holding shares of multiple keys on behalf of multiple users, and this can be advantageous from an efficiency point of view. So just to give you the picture so you see what's going on here, right? The picture on the left is what happens if you take one of these, if you take this deployment model where the user maintains one of their key shares, and here we have two different users. So those two different users each have their own share of their own key sitting on their phone, and then they've outsourced the other two out of the three shares to this other entity sitting in the cloud. Whereas on the right-hand side, you again have the two users with the two phones, but all those key shares are sitting on the same set of three servers that are running in the cloud. And what that means is that if you look at the picture on the left, then when the user on the left wants to sign, there's sort of a, let's say, 3 out of 3 TSS protocol going on among the three parties in the left oval. And when the user on the right wants to sign, you have a 3 out of 3 protocol running among the three parties on the right in the right oval. Whereas on the right-hand side, in the picture over there, you have the same set of 3 servers that are signing on behalf of both users. And so you have the same set of 3 servers that are running the threshold protocol. And obviously, this extends to more than 2 users who are signing, but there's a limit to what I could fit on the slide. So what are some efficiency advantages that you can get from these key management networks? Well, the server's state can be shared across executions involving different keys. And when I gave this talk, or when I gave my talk at Decompute last year, I talked about how that could be advantageous in the context of the CGGMP protocol to basically share some of the pre-processing that's done as part of that protocol among these servers that are all running many instances of the protocol. So rather than treating the instances completely independently, you can share some pre-processing information among the servers and avoid having to waste the effort every time you want to run the protocol using a different key. You can also take advantage of batch processing and utilize aggressive pre-processing to do a lot of the work that's needed in order to generate a signature before the message to be signed is even known. That's something that we see actually a lot in many solutions, but the point here is that you can do this, and I'll talk about this more in a few slides, but the point is now that you can do this not on behalf of a single key that's shared among those servers, but on behalf of the many, many keys that those servers are collectively sharing. And then, as I mentioned earlier, you can use more flexible thresholds, and in particular, you can at least imagine using an honest majority protocol rather than a dishonest majority protocol. And honest majority protocols in general are going to be much more efficient than what you can obtain for a dishonest majority protocol. So with that in mind, I want to now talk a little bit about honest majority threshold ECDSA. And I should say, in particular, for key management networks. So the kind of optimizations we're going to be talking about really only make sense in a network where you have the same set of parties who are running a threshold protocol on behalf of many different keys. So right, there are several prior works that have considered honest majority threshold ECDSA, but to the best of our knowledge, none of this prior work explicitly considers the setting where you have multiple users all sharing their keys among the same set of parties. And as a result, none of them explicitly consider batch pre-signature generation, and in particular, batch pre-signature generation of key-independent pre-signatures. And I'll talk in a minute about what key independence is and why that's important in our setting. And someone can correct me afterward if I'm mistaken here, but I have not seen anything prior that did this. Okay, so let's assume we have shares of private keys that are generated using some DKG protocols. So the key generation, the distributed key generation, is going to be out of scope for the purposes of this talk, but we'll just assume that it's been done already, and that we have some collection of servers that again all share these or hold these key shares for many different keys. So the way the system as a whole is going to operate is that first of all, we're going to have these servers initialize some long-term correlated state. That's going to be, think about that as a one-time operation that those servers are going to do, and then they're going to keep that long-term state fixed for, imagine the lifetime of the system. We can imagine refreshing it also, but it's simply just to think about it being done once and then having it available for the lifetime of the system. And then what we'll repeatedly do is the following 2 steps. So first of all, we're going to perform what I'll call batch pre-signature generation. So what that means is that the group of parties, this collection of servers holding all the key shares, is going to generate a large number of these so-called pre-signatures, which essentially means that they're able to do most of the work that's involved in signing in advance before any signing requests come in. So before the message to be signed, or before the messages to be signed, I should say, are known, and even before any of the keys that are going to be used to sign are known either. So that's what I'm referring to as this key independence property. So in a lot of the prior work, especially in the dishonest majority setting, when you generate these pre-signatures, they're tied to a particular key. So you generate a pre-signature for key number 7, and then you can only use that pre-signature to sign a message using key number 7. Whereas key-independent pre-signatures give you the ability to generate this pre-signature information that can then be used to sign with any of the keys that this network is holding. So we've generated this large number, I'll call it M, of the key-independent pre-signatures. And given that setup information, the servers can now sign up to M messages extremely quickly. So they can now, as signature requests come in, with each signature request being associated with a particular message and a particular key that's going to be used to sign that message, they can handle all of those signing requests until they use up the set of pre-signatures that they have. And after they've used up the pre-signatures, they go back to step 2 and perform the batch pre-signature generation again, and then they're ready once more to sign the next M set of signature requests that come in. So you get a picture of something like this here, where first, we generate the correlated state. This is some initialization phase that you can again think of as being done once and for all for the lifetime of the system. And then when needed, right, when they've exhausted their collection of pre-signatures, the servers will run this batch pre-signature generation protocol to generate M pre-signatures. And then they can handle up to M signing requests that come in before needing to refresh the set of pre-signatures that they hold. And I should note here that the key independence property is really critical to making batch pre-signature generation viable. So why is that the case? Well, your network that's holding all these key shares may be holding tens of millions of keys and issuing thousands of signatures per second, but you don't know in advance which key is going to be used to sign next, and you don't even know in advance which key is going to be used in the next 24 hours. Right? It's sort of a random distribution in some sense of which keys are going to be used to sign. And moreover, any given key may only be used very once in a while. So you're storing these tens of millions of keys, you're issuing, I don't know what it comes out to, some tens of thousands of signatures per day, but that means that any particular key may only be used once every 100 days. And so it wouldn't make sense, really, to generate a pre-signature for any particular key, and it would be rather expensive to generate sufficiently many pre-signatures for every key that your system is handling, right? That would involve, at the minimum, generating tens of millions of pre-signatures, one per key, and then most of those are never going to be used for the next year. Okay, so that would be very wasteful. So the key independence property allows you to avoid this problem, this bottleneck, generate those pre-signatures that are not tied to any particular key, and then regardless of which keys are going to be used to sign the next M requests, you can handle them using the pre-signatures that you've generated. So I'll focus here on just kind of the interesting bits of the protocol. I'll just talk briefly about the long-term state and how we initialize that, and then talk about the mechanism we use for the batch pre-signature generation. The online signing is kind of done in a standard way. I think I do mention it, but I don't really focus on it very much. It's kind of a standard mechanism. So I'll focus on these two first components of the protocol instead. So for the correlated state, we're going to use a technique that I think was introduced this morning as well. It's using the idea of what's called pseudorandom secret sharing, also pseudorandom zero sharing, which is a very nice technique that's suitable when you have a relatively small number of parties. Think about if you have less than 10 parties or so who are holding key shares, then you can pretty effectively use this technique. It doesn't scale to thousands of parties, but it is suitable for smaller networks. And it's a very nice technique. I'm not going to go into the math behind it, but it's really beautiful because it allows the parties, once they've set up this shared state, to then non-interactively generate t+1 out of n shares of random values and 2t+1 out of n shares of a value that's guaranteed to be 0. So it's a random sharing, but guaranteed to be of a 0 value. And both of those offer security against up to t corrupted parties. And these are very useful if you can set up the shared state among those servers, then it gives them a very efficient way to generate these random values that are useful during the course of a protocol. And at least as far as I've seen, and I'm again happy to be corrected if I'm mistaken, The prior work using pseudorandom secret sharing assumes that this correlated state is either set up by a trusted dealer or by some relatively complicated MPC protocol. And we observe actually that in this particular setting or for our particular protocol, it's actually secure if the parties set up the correlated state on their own. So what do I mean by this exactly? What I mean essentially is that, well, it's a bit complicated to get into without describing the entire protocol, but essentially you'll have designated parties in the network who set up the correlated state among certain subsets of the servers. And they can actually cheat if they're corrupted. They may cheat in the way they distribute the secrets, but it'll only affect correctness. It won't affect privacy. And the correctness will basically be caught later in the protocol, and so it's sort of not an issue for the overall security of the system. So before I get into the next part of the protocol on the batch pre-signature generation, I'll just briefly review ECDSA, mainly just to set up the notation I'm going to use. So we have a cyclic group of prime order Q with some fixed generator G. Any particular private key is going to be a random element in ZQ, and the corresponding public key will be Y equals G to the X. And then when you want to sign a hashed message a hash message H, so I'm going to assume the hashing has already been done, what you do is you choose a uniform nonce value K, you compute this value R equal to G to the K, and then you compute this mapping, which for ECDSA is just taking the X component of the elliptic curve point, and you compute some value little r from that. And then you compute this sort of complicated expression that Abhi talked about in his talk, which involves the inverse of K, which causes a lot of complications in threshold protocols for ECDSA. And then the final signature is just R and S. And in our setting here, I think I've used this notation already, but we have a total number of parties N. T is going to be an upper bound on the number of corrupted parties that the system can tolerate. And the fact that we're in an honest majority setting means that we're assuming that T is less than N over 2. And you can think about, if you like, actually just setting T to be the maximal value subject to that constraint. So if N is odd, you have T as the floor of N over 2. So the way the pre-signing is going to work is as follows. So at a high level, what we're going to do is we're going to use this technique of Beaver called multiplication triples, where you're going to generate this large number of multiplication triples, denoting them by AI, Ki, and Wi. And this notation where I put a value in brackets just indicates that that value is shared in a T out of N fashion among the servers controlling the key shares. So what we've done here is we've set up M different triples. Well, I guess the notation is bad because the bracket M means something different. But if you don't know what it is, you can just ignore it. But we have M of these triples, where every triple consists of 3 shared values, with the property that AI times Ki is equal to Wi. So none of those values, AI, Ki, or Wi, are known to any of the parties individually because all those values are secret shared. But it'll be shared subject to the constraint that the product of the first 2 is equal to the third. And then each party Pj, this is still during the pre-signing. So each party Pj will send for every I the value Wij, namely its share of Wi, as well as G to the Kij, so basically the share in the exponent of the K value, send that to all other parties. That allows the other parties to reconstruct the value of Wi and the value of capital Ri and compute little ri as well. And then every party will compute locally a key share K prime Ij equal to Wi inverse times Aij. And basically what this means is that if everyone proceeded correctly, that means that this K prime Ij is then actually a T out of N sharing of Ki inverse. And then the pre-signature, or the pre-signatures that the parties will output, consists of the value Ri, which now is public, all the parties know it, as well as the share of this value K prime. And they have M of these pre-signatures. So every pre-signature is just this pair, and each party has M of these pairs. And then you can sign a given message HI, so when a particular request for a signature comes in on some hash message HI using a particular key, right, that indexed by some value and represented here by X, I don't want to go into this actually because it's pretty standard, but if you do the math, you can see that you can use the value K prime that the parties have already shared in order to compute a signature very quickly. There's no interaction here between the signatures, between the parties. This is all a local computation. The parties do the local computation, they send their partial results back to a coordinator, and then the coordinator can reconstruct a signature from the information that it received. And it can also verify correctness of the signature as well. So how do we do the batch generation of multiplication triples? So we take inspiration from prior work on general secure computation in the honest majority setting, but we noticed a number of optimizations that we can apply in our setting. So first of all, as described and as used in the context of general secure computation, their technique actually does not allow for pre-processing because you actually check the computation as it's being done, so it needs to be done after you hold the input. But we observe, right, for ECDSA signing, pre-processing is possible, basically because we're using these multiplication triples that don't depend on the actual input. And moreover, maybe more interestingly, we can reduce the cost of their technique by about 25%. And roughly, this is because in the application to general secure computation, they need to maintain privacy of the values in the computation, even in case a fault is detected. Whereas in our setting, because we're only generating these random multiplication triples that have no connection to any key shares, we can afford to give up on privacy in case cheating is detected. Let's see, I'll go through this a little bit quickly. It's maybe not super important, but basically the way we handle the batch generation of multiplication triples is we rely on a subroutine for what's called weak multiplication of shared values, which ensures privacy but not correctness. And it's more efficient than doing a fully secure multiplication. And then we do a randomized batch checking of the results. And I think I'm going to just skip this slide, but this basically is in one slide how we do the batch checking. And I think the main takeaway, without going through all the math, is just that the cost of the checking is now amortized over the M pre-signatures that you generate. So you actually get much better amortized complexity as you increase the value of M, as you increase the number of pre-signatures you're generating. So this protocol that I described, well, let me just start with this actually. I mean, so this work was done as part of my work at Defense. And Defense had previously been using the CGG-MP protocol in a 3 out of 5 configuration. And actually the fact that they were using the protocol in a 3 out of 5 configuration meant that they were already in an honest majority setting. And therefore, we kind of observed that there was no point, if they're going to stick to that threshold, in using the CGG-MP protocol, which is tailored for the dishonest majority setting. So this honest majority protocol that I just described was developed and implemented in Rust over the past 1.5 years or so, and was recently deployed by Defense. And it's currently being used to host about 10 million keys and handle about 1 billion of transactions per month. And we have actually, well, this is something that just happened about a day or two ago, that Defense, in partnership with the Linux Foundation, has made available open source implementations of some of the TSS code that they've developed as part of what's called Lockness. It's a Defense-led initiative for open source cryptography, and we hope that many of you will pull from it as well as contribute to it. And I've put the URL there so you can all take a look and help make that community grow. So as far as performance, let's look at these are actual performance numbers in the Defense network for a 3 out of 5 threshold, assuming a 50 millisecond network delay. So actually, I shouldn't say that. This corresponds to what's in the Defense network, but these were experiments that were done where we could actually twiddle with the network delay to see how the communication delay would affect the performance of the protocol. So the first thing I just want to show is that the online signing time is kind of not the issue here, right? We're trying to really optimize the offline pre-signature generation time. The online signing times for both CGG-MP and our protocol are 50 milliseconds. And the reason for that is because they're bounded by the network delay. So if we look at just the computation and not including the network delay, you get something on the order of 1/100th of a millisecond. And it's really going to be dominated by what's done during the pre-signature computation phase. As for the pre-signature generation itself, when we have a batch size of 1, so in that case, there's not really any amortization going on, you can see that the honest majority protocol I just described is already outperforming the CGG-MP protocol by roughly a factor of 2.5. And the numbers get better as M gets larger. So if we set the batch size to about 10,000, The CGMP protocol actually doesn't take advantage of any batching, so you get the same number of 1500 amortized time for pre-signature generation, but our protocol is generating pre-signatures at the rate of only 1.3 milliseconds per pre-signature. And just to kind of give a reference, if we do the same thing but with no network delay, so just looking at the computation time itself, actually you get barely any change. I mean, you get a change in the CGMP protocol, but in our case, since we're anyway amortizing over a large number of signatures, it sort of gets washed away, and you get something. You get numbers like these. Yeah, good. So just to summarize, these key management networks, I think, are really a powerful paradigm for deployments of threshold cryptography, and I think maybe other people want to consider that paradigm and explore further optimizations within that sort of a deployment scenario. And then I also talked about a fast, honest majority ECDSA protocol that offers the ability to generate for batch pre-signature generation with key independent pre-signatures. So thank you, and I'm happy to take any questions that you may have.
Hi, John. So who picks the committee to sign a message?
So the way that it's set up, I mean, you're asking in the defense network or in general?
In general.
Okay, well, in general, anybody can pick it. I mean,
the user? Is it the user?
So no. So, well, okay. I mean, you could have it. You could imagine the user doing it. The way we currently have it set up in the defense deployment is that there's a coordinator who handles requests from the user, and they're kind of picking basically which subset of the parties of the network to sign, and they're doing it, using some load balancing technique.
So I'm asking, like, if the coordinator can be malicious, then it might use different, like, separate parts of the network to send on the same message, but with different nonce. Is it possible?
So there is. I mean, I'm not sure exactly what you meant. There is a possibility that the coordinator could send different hash messages to different parties. Maybe that's what you mean?
No, I'm sorry. There is the attacks of sending two different messages with the same nonce. So this is what
no, that can't happen because each pre-signature is used once and then it's thrown away. So you would never reuse a pre-signature. So if you have like party 1 using pre-signature 1 and party 2 using pre-signature 12, then you just get garbage. And once party 1 uses pre-signature 1, they delete it and never use it again. So you can't get nonce reuse.
So each party will announce on the nonces that it uses to the entire network every time?
The coordinator actually tells it which nonce to use, and so the coordinator is making sure that all the parties are using the same nonce. But if the coordinator tells party 1, if the coordinator tells party 1 use pre-signature 1, and then again tells it to use pre-signature 1, that party will say, no, I already deleted it, I don't have access to it.
But a coordinator can split the network and tell each part of the network to send on different message, but they are actually using the same nonce.
So right? I think if you did a 2 out of 5, that would be possible, but in a 3 out of 5, it's not because there's an overlap.
Right.
But it's a good point, actually. If you have lower threshold, it's a good thing to be careful about.
Mm-hmm. Okay, thanks.
I have a question. Yeah. So
I can't see where the question. Oh.
Yeah. So I'm curious if the check on the beaver triples for correctness is necessary. Like, is that an attack if you remove the correctness check?
I would have to think about it. I'd have to think about it. I mean, I think that at the minimum, I would say the proof. I don't see how the proof would go through, but I would have to think about it. Actually, I don't know. I don't know the answer off the top of my head. Do you think there's a reason that it would be secure even without the check? Because I guess the point is that then the only property you get from the weak multiplication. The adversary can introduce an additive shift into the multiplied value, and it just seems that I don't know how to handle that in the proof, I suppose.
I can think of an alternative way to do it that maybe doesn't need this.
Okay, I'd be happy to talk about it then. Yeah,
thanks.
Great.
How does it work? Does the user first authenticate to defense, and then defense picks 3 servers among its fleet and just says signature for that?
Yeah. Yes. I mean, you can have, well, I'll see where your question goes, but you know, you can have, for example, you can have policies behind the shares themselves. So like, you know, you'll only issue a signature under XYZ constraints, but yeah, basically that's how it works. Oh yeah, right. So that's number one, is that it's defense making sure there's no single point of failure. But number two, and geographically as well, because these servers can be geographically distributed as well. But also, I guess a longer term goal is to have those servers actually managed by different entities. So they wouldn't even all be managed by defense. They would have a partnership with Amazon who would run one of them, for example.
Yep, I think we are done with the questions. Please give a big round of applause for Jonathan Katz.